When ordinary iron is left exposed to the elements, it begins a slow, inevitable decay. It flakes, it pits, and under enough physical stress, it eventually disintegrates. Most metals have a clear point of failure, yet we build machines that operate in environments that should destroy them, from the searing heat of jet turbines to the high-pressure salt water of the deep ocean. These technologies rely on the specific properties of element 28. This is nickel, a dense, silvery white transition metal. On the periodic table, you'll find it at atomic number 28. Its atomic structure allows it to maintain its integrity where other materials warp or shatter, serving as a bridge between structural failure and engineering success. Nickel naturally forms a microscopic oxide layer on its surface. This barrier stops corrosive chemicals and salt water from penetrating the metal, making it virtually immune to rust. It is also remarkably stable at high temperatures. While other metals soften and lose their shape, nickel keeps its strength even when glowing red-hot. Beyond its strength, it is one of the few elements naturally magnetic at room temperature, a rare trait shared by only two other elements on the periodic table. This combination of corrosion resistance, thermal stability, and magnetism makes it a primary choice for hardware that must survive at the edges of physical endurance. In the 18th century, German copper miners began finding veins of a metal they couldn't identify. They pulled up a dense, reddish ore that looked like copper, but when they attempted to smelt it, the rocks refused to melt down and produced no usable metal. The miners, frustrated by the useless rock, blamed mythological sprites. They nicknamed the material Kupfernickel, or Old Nick's copper, suggesting the devil had cursed the mine. It wasn't until 1751 that chemists isolated the substance. They discovered it wasn't a failure of smelting, but a distinct, stubbornly durable element. The miners were right about the metal's stubbornness. It was the first sign of the unbreakable atomic bonds that would eventually define its industrial use. Modern engineering doesn't use nickel for what it can do alone, but for how it reinforces other metals in complex alloys. By adding nickel to iron and chromium, we create stainless steel, a material that brought rust-free durability to everything from surgical tools to modern skyscrapers. In aerospace, nickel-based superalloys were developed to survive the intense combustion inside jet engines, allowing them to run at temperatures that would liquefy standard steel. In industrial chemical manufacturing, massive processing towers and pipe networks are lined with nickel to handle corrosive acids that would otherwise dissolve the facility from the inside out. Nickel provides the structural reinforcement that allows our most critical machines to withstand the forces we put them through. We are now moving beyond large-scale mechanical engineering and into the microscopic chemistry of energy storage. Inside a lithium-ion battery, energy is stored in a cathode. As lithium ions flow in and out, the structure can become unstable. Nickel acts as stabilizer, holding the framework together so the battery can be charged and discharged thousands of times. High concentrations of nickel are what allow batteries to achieve the energy density required for long-range electric vehicles and high-performance electronics. It is the chemical anchor that makes it possible to safely pack immense amounts of energy into a compact space.
The same element in this coin is currently holding together the combustion chambers of jet engines and the internal grids of our electric vehicle batteries. Nickel operates where the pressure is highest, ensuring the systems we rely on can endure the most extreme conditions humanity has created. And as we push the limits of our technology even further, we turn to the element that the 18th century miners found right next to it, element 29, copper.